All right, in chapter 2, we're going to start talking about our location that we fall in a distribution. So a couple of examples would be like when you take the ACT test, you'll be given a score and what percentile that you fall at. And other ways we could look at is any classroom situation we could look at a test. The difference is we'll get into a normal distribution. ACT scores are generally normally distributed. I can take any type of distribution and tell you what percent you fall at. So percentile, one of the things that we want to know is that this percent below. Okay, it's always percent below. And one of the things that's going to happen is if, say, we had a test out of 30 points, you scored 25. We are going to talk about what percent of people scored less than 25. We don't care about the percent of people who scored 25. We don't care about the percent of people who scored above 25. We talk about the percent that scored below. So when you're told that you're at the 75th percentile, that means that you scored better than 75% of the rest of the people taking a test or doing whatever we're dealing with here. So one of the ways we can make some comparisons with this as well is if we talk about standardizing a score. Okay, and so standardizing, what we're saying is I want to put it in terms of some size. And so we talk about it as a z-score. And so what this will allow me to do is I can compare someone who's taken an ACT test versus an SAT test. I can compare males versus females in some event in different situations. And how I calculate my z-score is by taking x minus my mean, and we'll get notation for this in a bit, divided by my standard deviation. Or in other words, I talk about as my observation minus my mean, divided by my standard deviation. What we're saying is we want to break things into the size of my standard deviation. So for instance, if I take a pizza and I cut it into eighths, that means I'm cutting it into 8 equal sized pieces. If I cut it into quarters, that means I'm 4 equal pieces. When I cut it into, say, my standard deviation is 2.5, I'm cutting it into basically chunks that go up and down by 2.5. Okay, and so what we're looking for, for instance, if I'm comparing somebody who took an ACT score or an ACT test, an SAT test, is which one scored higher above the mean in terms of how many standard deviations again. Okay. Another thing we'll look at is transforming my data. Okay, so now I know where I fall, but what happens if in a situation I decide to change the scores on a test? Okay, a number of people talk about curving a test by taking the highest score and adding, say, 4 points to the highest one to make it perfect. Okay, how does that change things? Well, if I add the same value to every one of my observations, okay, these will change as well, your location. So when we talk about locations, my mean, I would add 4 to my old mean to get my new mean. I would add 4 to my old median to get my new median. To my quartiles, my min, my max, everything would move up 4. The shape of your distribution would remain unchanged. It's going to stay the same. Okay. Measures of spread. If I move my minimum up the same and then my maximum up the same, that distance between them doesn't change. So range, interquartile range, standard deviation, when I just add, that always remains the same. Okay. Now, what if, though, for some reason I decide that take a test that's out of 50 and double it, so now it's out of 100 points. Okay. Now, what will happen is these location pieces, again, will change. Okay, so if I had 42 out of 50 and I double it, now I'm at 84 out of 100. Okay, so I'm doing the same thing to the originals as I'm doing to the rest of my data. My shape will still stay the same. And again, talking about shapes, symmetric, skewed, neither, whatever like that. But now if I change my minimum, say my minimum originally out of 50 was 10, now that goes to 20. Say the maximum was 50, now it's 100. So originally it was 10 to 50, which is 40. Now it's 20 to 80, it's 100. It also doubled. So my measures of spread will also change if I multiply all the values in a data set. We'll eventually look at what if I do both. Okay, how do I know what's going to happen? All right, density curves. Density curve, what it is, it's a smooth curve, okay, that represents what my data looks like. What I talk about a lot of times is if you think about it, if you have a histogram or something, if you took and put a point at the top of each bar, okay, and what you basically do is you're playing dot to dot. Okay. Now, the other thing, it has to always get to my x-axis. Okay, so all I'm going to do is continue it down until it gets to the x-axis. And this would be an example of a density curve. Okay, now it's not a very good one because a lot of times what we'll do is we'll just kind of estimate what it's going to look like. So I'm short here, so I'm just going to kind of go, and I don't have to hit every middle exactly. Okay. So over here with this distribution, obviously you can kind of see that this is a distribution that's skewed to the left because I have that tail on the left again. Okay, and so if I kind of go, one of the things I don't want to do is go bump and bump back up. Okay, so I can just skip that and just kind of keep it going, but then again bring it back down to your x-axis. Okay, so now we want to talk about where's my mean and median in these distributions. Okay, now the nice thing is that your mean and your median on a symmetric distribution are always going to be at the same place. Okay. When we get to skewed, it's a little different. You got to remember, and I'm going to start with the median because that's the midpoint. So basically what I'm kind of thinking about is if I take this bar here, I'm going to try and kind of balance them out. Okay, so those three on the bottom kind of undid the one on the top. Bring this one here and bring this one here. Okay, so my median is going to be somewhere in this region. Okay. Okay, so we talked about my median being about in here somewhere. Because basically it's just like when you found it in a set of data. I took and crossed off my smallest value, my largest value, my next largest, and my next smallest. Now my mean though, again, remember is not resistance to outliers. So what happens with my mean is it gets pulled towards the tail. Now a lot of times what they'll talk about is this is a balance point. If I were to put a fulcrum here and make this histogram out of something solid like bricks or and put them on a teeter-totter, how would that balance out? And remember, if I have a person and another person on a teeter-totter and the bigger person has to sit closer or the smaller person has to sit farther away to make it balance, same kind of idea. It's kind of your balance point. All right, so that takes care of section 1.